Unlike manual spreaders, where operators can adjust output primarily through truck speed, conveyor speed, or gate height, some computerized ground speed controlled systems include adjustment settings that can help fine-tune material output based on measured performance. Depending upon the controller system, adjustment terminology may vary. Some systems may use terms such as rate adjustment, calibration multiplier, material factor, or product adjustment. Other systems may use guided calibration routines or manufacturer-specific procedures instead of direct factor entry. Significant differences between target and actual output may indicate a controller adjustment is needed, a material setting is incorrect, a maintenance issue exists, or manufacturer-supported recalibration is required. On some systems, operators or mechanics may be authorized to make adjustments directly. On others, access may be restricted to supervisors, mechanics, vendors, or manufacturers. Always follow your agency's policy and your equipment manufacturer's recommended procedures before making controller adjustments. Because real-world conditions do not always match factory assumptions, computerized ground speed controlled spreaders require periodic verification and recalibration. Chain tension, wear to mechanical components, auger conditions, spinner performance, gate settings, and material characteristics all influence how material flows through the system. Calibration and verification help confirm that actual material output reasonably matches intended application rates under field conditions. We'll first measure output using a stationary check. This verifies that the spreader can physically produce the expected discharge rate under controlled conditions. Material is collected over a timed period, typically 30 seconds, and converted to pounds per minute. For computerized systems, we compare what the system is set to apply versus what it actually produces. For consistency, our check uses a 20 mile per hour reference speed. At 20 miles per hour, each pounds per lane mile preset corresponds to an expected pounds per minute discharge rate. This will require the system to be placed in a calibration mode or manual mode to bypass the ground speed controls since the vehicle is stationary. The vehicle's RPMs should be brought to between 1,300 and 2,000, which is dependent on normal operating RPMs for 20 mile per hour travel. We then run 3 30-second time captures and use the average of those three, convert to pounds per minute, and then compare actual output to expected output. Through this, we can determine if within reason the spreader is physically producing the required discharge rate under stationary conditions. However, this does not confirm how accurately the system responds while the truck is moving and speed is changing. Ground speed controlled systems continuously adjust output as a vehicle speed changes. Therefore, the moving check will verify whether the system is maintaining the correct application rate while the truck is in motion. There are several ways to complete a moving check, ranging from highly accurate weighing methods to more practical field estimates. If your agency has access to a loader scale or vehicle scale, one of the most accurate methods is in-storm testing using actual material weight. To complete this test, determine how much material is in the truck before the route segment, run the route under normal operating conditions, determine how much material remains after the route, calculate the total material used, and divide by lane miles treated to determine actual pounds per lane mile. If scales are not available, a loader bucket estimate of what you start and end with can provide a practical field check. For example, if your loader bucket typically holds about 3 tons of salt, one full bucket would contain approximately 6,000 pounds of material. If you returned with about 1/3 of a bucket remaining, you would estimate roughly 2,000 pounds still left in the truck. That means you used approximately 4,000 pounds or 2 tons during the route and could compare that to your miles treated and expected usage. This method is less precise than scale-based testing. Bucket fill levels can vary, and material density and moisture content affect weight. However, it is still a useful practical method for identifying whether the spreader appears to be significantly over-applying or under-applying material. Another option for moving verification is the sweep test. Unlike live route testing, sweep tests can be completed in a controlled area, such as a yard or parking lot, often during your pre-season setup. To complete a sweep test, apply material over a measured distance, run the truck at operating speed and preset, recover as much material as you can from the test area, weigh the recovered material, and calculate the pounds per lane mile. This provides another way to verify in-motion performance under controlled conditions. There are also several simple day-to-day field checks operators can use to help identify potential issues. These include comparing truck speed to controller speed, confirming the spreader discharge stops when the truck stops, observing whether the output changes as speed changes, reviewing controller logs or route data, and comparing total material used to expected usage. These are not formal calibration methods, but they can help identify systems that are not performing as expected. On the stationary check tab, we enter data fairly similarly to how we do a timed test for a manual spreader, but we include the preset application rate along with the three 30-second timed captured weights. The spreadsheet averages the capture values, converts the 30-second captures to pounds per minute, and compares actual output to the expected pounds per minute target at the 20 mile per hour reference speed. At 20 miles per hour, the truck travels 1 mile in 3 minutes. So throughout the process, the spreadsheet converts pounds per lane mile into pounds per minute for those comparison purposes. This allows us to verify that the spreader can reasonably produce the required discharge rate. On the Moving Check tab, we enter the preset application rate based upon lane miles, the type of moving test we performed, in storm or sweep, the test speed in miles per hour, the travel distance, and units. In a sweep test, you'd likely be entering feet here, and in an in-storm test, miles, and you'll enter the starting and ending material weights. This spreadsheet will then calculate the total material used, the actual pounds per lane mile, and the difference reflecting how the actual output compares to the preset. For our moving test example, let's assume we treated 5 miles of roadway out and back, or 10 lane miles total, at 250 pounds per lane mile as part of an in-storm test. First, we would enter our gate height and our truck number. Next, we'll enter our preset 250 pounds per lane mile. And we'll note that it was an in-storm test option and that we were testing at 25 miles per hour and we treated 10 lane miles. One thing to note, if we had treated one pass down the center line but had doubled our application rate to do so, we'd want to note the proper application rate of 500 pounds per lane mile as our preset. Now over in column H, let's indicate how many pounds of material we started with, assuming we weighed out 3,500 pounds of material into the truck, and then we came back and offloaded and determined that we came back with 700 pounds of material left over. The spreadsheet calculates that we therefore applied about 2,800 pounds in that 10 miles of roadway, resulting in an actual pounds per mile of 280, slightly above our 250 preset rate. The spreadsheet also calculates an adjustment ratio by dividing the target application rate by the actual measured output. In our case, we're about 11% over target and would need to make adjustments to correct for that. Different controller systems use this information differently. Some may use a multiplier, a percent adjustment, a guided calibration routine, or other manufacturer-specific adjustment method. The calculated ratio helps identify the size and direction of the correction needed, but it is not necessarily the exact value entered into the controller. Always follow manufacturer procedures and agency policies before making adjustments. If your system does not allow operator-level adjustment access, or if agency policy restricts changes to controller settings, operators should still take practical operational steps to help manage application rates safely and responsibly until the system can be properly adjusted or serviced. Depending on agency policy and equipment design, this may include adjusting the gate height, if permitted, reducing vehicle speed where appropriate, using a lower preset application rate, monitoring material usage more closely, or reporting significant over-application or under-application to supervisors and mechanics. Even on computerized systems, operators should continue using observation, judgment, and field awareness to help ensure material use remains reasonable and effective. After any adjustment is made, the system should be retested and verified. For example, if retesting shows a target of 250 pounds per lane mile, measured 225 pounds per lane mile, 250 divided by 225 equals 1.11. This indicates the system is now slightly under applying material. Calibration is often iterative. However, if significant inaccuracies continue after repeated verification attempts, that may indicate a mechanical issue, a material flow problem, or a controller issue requiring maintenance or vendor review. Menus, terminology, adjustment methods, and access levels vary across manufacturers and controller systems. However, the general verification process remains similar. Measure actual output, compare actual output to target application rate, determine whether adjustment or maintenance may be needed, follow manufacturer and agency procedures, and retest to verify performance. Recalibration should be performed whenever conditions change in a way that may affect material flow. Examples include switching materials, equipment repairs, mechanical adjustments, start of a new season, or noticeable changes in performance or material usage. Any condition that changes how material moves through the system can affect calibration accuracy. In summary, stationary checks verify the spreader can produce expected output. Moving checks verify the system maintains the correct rate in operation. In-storm weighing is one of the most accurate verification methods, but bucket estimates and sweep tests can be practical field alternatives, and verification helps confirm that actual field application reasonably matches intended application rates.